So the alternating sequence theorem can be a really useful theorem when the terms in your sequence are alternating signs, or even just, so alternating signs implies that it's each consecutive term has a different sign. Maybe just some terms are negative, some terms are positive, and sometimes it's more convenient to look at a sequence of just all positive terms, so to take the absolute value. Alternating sequence theorem says if you take the absolute value of every term in the sequence and that sequence of positive terms is approaching zero, then the limit of the original sequence is also zero. So the original sequence converges to zero. The proof of this is a nice application of the squeeze theorem for sequences. And so I wanted to show that here. So let's assume that this AN is a sequence where this statement is true, where the limit as n approaches infinity of the absolute value of each term converges to zero. Then the terms in the original sequence AN, there, let's say this. Note that, so the terms in the original sequence AN must be less than or equal to absolute value of AN, right? Because two cases to consider here. Either AN is negative, in which case this is definitely less, or AN is positive, in which case these are both positive and they're equal. Okay, so that's true. And like I said, I'm heading towards, I want to apply the squeeze theorem. So I want to put something on the other side so I can squeeze the terms in this AN sequence between two other sequences. So similar idea here. If this is always positive, then AN is either positive and they're equal, or it's negative and it's less. What about negative absolute value of AN? So those terms are always negative, because this absolute value will always be positive. You stick a negative in front, that's always negative. So with comparing with AN, either AN is negative, and these guys are actually equal. Like say AN is negative 3. You take the absolute value, that's 3. You stick a negative in front, it's negative 3 again. So if AN is negative, these guys are equal. If AN is positive, then this is certainly bigger. So this will be true for all positive integers n. Just because of space, I'm going to put for all n here. Also, I'll put and, so forget this period for a minute. The limit as n approaches infinity of, well, let's take the limit on this side. The limit as n approaches infinity of the absolute value of an. This is the one that we're assuming is equal to 0. So this is approaching 0. Also, if you take the limit of negative absolute value of an, well then here you could just move the negative in front, and then it's the limit as n approaches infinity of absolute value of an, which we just said is 0. So if, that's my red, if the limit as n approaches infinity here is 0, the limit as n approaches infinity here is 0, then the terms in the middle here must also be approaching 0 by the squeeze theorem. So I haven't written out everything formally, but now we know by the squeeze theorem that the limit in the middle must also be approaching 0 by the squeeze theorem.